Welcome to this coding problem walkthrough. In today's session, we'll explore problem number 1064, fixed point. We'll discuss its requirements, analyze the problem step by step, and work through potential solutions. Let's dive right in. In this problem, we are looking for what's called a fixed point in a sorted array of distinct integers. A fixed point is an index I where the value of the array at that index, I, is equal to the index itself. Our task is to find the smallest such index I and return it. If no such index exists, we return -1. The input to the problem is a single sorted array of integers, and the output is an integer that represents the smallest fixed point or -1 if there isn't one. For example, consider an array like -10, -5, 0, 3, 7. Let's explore how to solve this with examples. In the first example, the input array is -10, -5, 0, 3, 7. Here, the output is 3 because at index 3, the value of the array is 3, which satisfies the condition I equals I. This is the smallest index where the condition holds true, so the result is 3. Now consider another example where the input array is 0, 2, 5, 8, 17. The output here is 0, because at index 0, the value of the array is 0, which again satisfies the condition. Since 0 is the smallest index, the result is 0. Let's look at a third example to understand when no fixed point exists. If the input array is -10, -5, 3, 4, 7, 9, the output is -1. In this case, there is no index I where the value of the array matches the index. For instance, at index 2, we have 2 equals 3, which does not equal 2. Similarly, none of the other indices satisfy the condition, so we return -1. Moving on to the constraints, the length of the array can range from 1 to 10,000, and the values can range from -10⁻9 to 10⁻9. Additionally, the array is always sorted in strictly increasing order. These constraints are important to consider when designing an efficient solution. Finally, let's address a couple of edge cases. If all elements in the array are negative, it is impossible for any index to satisfy the condition I equals I, so the output will always be -1. For example, if the array is -10, -5, -1, no fixed point can exist. Another edge case occurs when no index satisfies the condition at all, as we saw earlier, and in such cases, the output should also be -1. These observations can help us reason about the problem and handle special scenarios correctly while implementing the solution. To begin solving this problem, let's consider the brute force approach. The intuition here is straightforward. We iterate through the entire array and, for each index I, check if the condition I equals I holds true. If it does, we return that index immediately. If no such index is found after completing the loop, we simply return -1. While this approach is simple to understand and implement, it can become inefficient for larger arrays. Now, there are some key observations that can help us refine this process. First, because the array is sorted in ascending order and all elements are distinct, we can leverage specific properties. For instance, if at any index I, the value I is greater than I, it means no fixed point can exist in the subarray to the right of I. Similarly, if I is less than I, it eliminates the possibility of a fixed point in the subarray to the left of I. These observations suggest that instead of checking every element, we can narrow down our search range using a more efficient method. This brings us to the optimized binary search approach. The intuition here is to use the sorted property of the array to quickly locate the smallest index I where I equals I. By eliminating large sections of the array in each step, we can significantly reduce the time required to find the fixed point, if it exists. The binary search algorithm for this problem starts by initializing two pointers, left, set to the beginning of the array at index 0, and right, set to the last index, n1. We then calculate the middle index as mid equals left plus, right left, //2. From here, we compare the value at mid with the index mid. If mid equals mid, this means we have found a fixed point. However, since we are tasked with finding the smallest fixed point, we store mid as a potential answer and continue searching in the left half of the array to see if a smaller fixed point exists. On the other hand, if mid is less than mid, it implies that no fixed point can exist in the left portion of the array up to and including mid. In this case, we move the left pointer to mid plus 1 to focus on the right half. Similarly, if ARR, mid, is greater than mid, it means no fixed point can exist in the right portion starting from mid. Thus, we move the right pointer to mid 1 to search the left half. The process continues until the left pointer exceeds the right pointer, at which point the search ends. If we haven't found any fixed point by then, we return -1 as the result. When deciding between the brute force and binary search approaches, the primary factor is time complexity. The brute force method has a time complexity of O(n), because it requires checking every element in the array. In contrast, binary search takes advantage of the array's sorted property to reduce the search space logarithmically, resulting in a much faster O log n time complexity. Both approaches share the same space complexity of O(1), as neither requires additional data structures or memory. However, the performance difference becomes significant for large arrays. For example, if the array has 100,000 elements, binary search completes the task in just about 17 iterations, whereas brute force would require examining all 100,000 elements. This makes binary search far more efficient for large datasets. That being said, there are trade-offs to consider. Brute force is simpler to implement and may be sufficient for small arrays, where the difference in execution time is negligible. Binary search, while slightly more complex, is the better choice for large inputs due to its scalability. It's also worth noting that if the array weren't sorted, binary search wouldn't be applicable, and brute force would be the only viable option. The key insight here is recognizing that the sorted nature of the array allows us to eliminate large portions of the search space, which dramatically improves efficiency. In conclusion, binary search stands out as the optimal approach for solving the fixed point problem. Its logarithmic time complexity leverages the sorted property of the array, making it highly efficient for large inputs. While the brute force method is simpler and may suffice for smaller datasets, binary search strikes an excellent balance between performance and complexity, especially as input size grows. By narrowing the search space with each step, this method minimizes computation while maintaining accuracy, making it the ideal solution for this problem. In this problem, we are tasked with finding a fixed point in an array. A fixed point is defined as an index I where the value at that index is equal to the index itself, meaning ARR I equals I. If there are multiple fixed points, we can return any one of them. If no such index exists, we return -1. To approach this, we first need to understand the problem and its constraints. The array can include both positive and negative integers, and the values are not guaranteed to be within the range of valid indices. This means some values could be negative, or even much larger than the highest index in the array. Additionally, the array may have duplicate values. Once we have this understanding, the simplest approach to solve the problem is a brute force method, where we iterate through every index in the array and check whether ARR I equals I for each one. Now, let's dive into the brute force algorithm and analyze how it works. To implement the brute force approach, we begin by initializing a loop that iterates through all indices of the array, starting from I equals 0 and ending at I equals n1. For each index, we check if the condition ARR I equals I is satisfied. If we find an index where this condition holds true, we immediately return that index since it qualifies as a fixed point. If we complete the iteration without finding any such index, we return -1 to indicate that no fixed point exists. From a complexity standpoint, this algorithm is straightforward. It requires a single pass through the array, making the time complexity O(n). Additionally, since no extra data structures are used, the space complexity is O(1). While the brute force method is simple to implement and understand, it is not the most efficient solution in all cases, especially when the array is sorted. However, it is a good starting point to understand the problem. To optimize our approach, we can leverage some key insights about the problem. First, any value in the array that is outside the range 0 and 1 cannot possibly satisfy the condition ARR I equals I. For example, negative numbers or values greater than the highest index of the array can be ignored right away. This insight helps us focus only on relevant values. Additionally, there are some edge cases to consider. For an empty array, we should immediately return -1 because there are no indices to check. Similarly, if the array contains large negative numbers or out-of-range values, we can skip those without any further checks. In cases where multiple indices satisfy ARR, I equals I, the problem allows us to return any one of them. These observations not only help in refining the brute force approach but also set the stage for more efficient algorithms that take advantage of specific properties of the input. If the array is sorted, we can take a more efficient route by using a binary search approach. In this method, we start by initializing two pointers, low at 0 and high at n1. While low is less than or equal to high, we calculate the middle index mid as low plus high //2. At each step, we compare ARR mid with mid. If ARR mid equals mid, we return mid since it is a fixed point. If ARR mid, it means any potential fixed point must lie in the left half of the array, so we update high to mid 1. Conversely, if ARR mid, we search the right half by setting low to mid +1. This binary search approach significantly reduces the search space, making the time complexity O log n. The space complexity remains O1 since no additional memory is used. However, this method is only applicable if the array is sorted, highlighting the importance of adapting algorithms to the properties of the input. For both the brute force and binary search approaches, the input array itself is the only data structure used. This ensures minimal memory usage. To better understand the algorithm, let's walk through an example. Consider the input array ARR equals -3, 0, 2, 3, 5. Starting with the first index, I equals 0, we check if ARR 0 equals 0. This is false because -3 equals 0. Next, we move to I equals 1 and check if ARR 1 equals 1. Again, this is false as 0 equals 1. Then we move to I equals 2 and check if ARR 2 equals 2. This time, the condition holds true, so we return 2. This demonstrates how the algorithm identifies a fixed point as soon as it finds one, without needing to check the remaining indices. This efficiency is a key advantage of the algorithm's design. Now, let's look at another example to understand the failure case. Suppose the input array is ARR equals 1, 2, 3, 4, 5. Starting with the first index, I equals 0, we check if ARR 0 equals 0. This is false because 1 equals 0. We continue checking all other indices in the array, but in each case, the condition ARR I equals I is not satisfied. After completing the iteration and finding no fixed point, the algorithm returns -1. This example highlights how the algorithm gracefully handles cases where no solution exists, ensuring correct output in all scenarios. By considering both success and failure cases, we can see that the algorithm is robust and reliable, regardless of the input. The provided implementation solves the problem of finding a fixed point in a sorted array efficiently using a binary search approach. Here's the detailed explanation. 1. Initialization. The method begins by defining two pointers, left and right, which represent the boundaries of the array. Initially, left is set to 0, start of the array, and right is set to the last index of the array, len, ARR 1. 2. Binary search loop. A while loop runs as long as left is less than or equal to right. This ensures that the search continues until the range is exhausted. 3. Midpoint calculation. The midpoint of the current range is calculated as left plus right, //2. This avoids potential overflow issues that can occur with left plus right, /2 in other languages like C++. For fixed point check, the value at ARR mid is compared to the index mid. If ARR mid equals mid, a fixed point is found, and the method returns mid immediately. If ARR mid, it means the fixed point, if it exists, must be in the right half of the array. Therefore, the left pointer is updated to mid +1. If ARR mid, the fixed point must be in the left half of the array. Hence, the right pointer is updated to mid 1. 5. Conclusion. If the loop exits without finding a fixed point, the method returns -1, indicating that no fixed point exists in the array. This binary search approach ensures a time complexity of O log n, which is much more efficient than a brute force O n solution. The algorithm leverages the sorted property of the array to eliminate half the search space at each step, making it well suited for large inputs. Additionally, the space complexity is 1, as the solution operates in place without requiring additional storage. Here, we are implementing a solution to find the fixed point in a sorted array using binary search. The method fixedPoint takes an integer array as input. We start by initializing 2 pointers, left at the beginning of the array and right at the end. The while loop continues as long as the search space is valid, that is, while left is less than or equal to right. Inside the loop, we calculate the middle index using left plus right left /2, which avoids potential overflow issues that can occur with left plus right /2. Now, if the value at the middle index is equal to the index itself, we found the fixed point and return it immediately. On the other hand, if the value at ARR mid is less than mid, it means the fixed point, if it exists, must be in the right half of the array. So, we move left to mid plus 1. Otherwise, if ARR mid is greater than mid, the search narrows to the left half, and we update right to mid 1. If the loop exits without finding a match, we return -1, indicating that no fixed point exists. Finally, the main method demonstrates this solution with 2 test cases. In the first test case, the fixed point is found at index 3, and in the second, it is found at index 0. The main method continues with one more test case to further illustrate the function's behavior. Here, we use the array -10, -5, 3, 4, 7, 9. When the fixedPoint method is called, it evaluates this array and does not find any index where the value matches the index itself. As a result, the method returns -1, indicating that no fixed point exists in this case. This demonstrates that our binary search approach is efficient and correctly handles scenarios where the fixed point is absent. With this implementation, we achieve a time complexity of O log n, which is much faster than a linear search, especially for larger arrays. To solve the fixed point problem, we need to identify the smallest index I in a sorted array where the value at that index, ARR I, equals the index itself. If no such index exists, we return -1. The most efficient way to approach this is by using a binary search, which reduces the time complexity to O log n. Let's walk through an example to understand this process. Consider the array -10, -5, 0, 3, 7. Initially, our search range spans the entire array, so left is 0 and right is 4. In the first iteration, we calculate the middle index as 0 plus 4, //2 equals 2. At this index, the value is 0, which is less than the index value 2. Since the value at mid is less than mid, we focus our search on the right half of the array by updating left to mid plus 1, which is 3. In the second iteration, the new midpoint is 3 plus 4, //2 equals 3. At this index, ARR 3 equals 3, which satisfies the condition ARR I equals I. Therefore, we found a fixed point at index 3, and we return 3 as the result. Now let's consider a second example with the array 0, 2, 5, 8, 17. Again, we start with the entire array, setting left to 0 and right to 4. In the first iteration, the midpoint is calculated as 0 plus 4, //2 equals 2. The value at this index is 5, which is greater than the index 2. When the value at mid is greater than mid, it means any potential fixed point must be in the left half of the array. So, we update right to mid 1, which becomes 1. In the second iteration, the new midpoint is 0 plus 1, //2 equals 0. Here, the value at index 0 is 0, which matches the index itself. This satisfies the condition for a fixed point, so we return 0 as the result. This example demonstrates how binary search efficiently narrows down the search range to find the smallest fixed point. Finally, let's analyze the array -10, -5, 3, 4, 7. Starting with left equals 0 and right equals 4, the midpoint in the first iteration is 0 plus 4, //2 equals 2. At this index, the value is 3, which is greater than the index 2. Since ARR mid, we restrict the search to the left half by updating right to mid 1, which becomes 1. In the second iteration, the midpoint is recalculated as 0 plus 1, //2 equals 0. Here, the value at index 0 is -10, which is less than the index 0. When the value at mid is less than mid, we shift our search to the right half by updating left to mid plus 1, which becomes 1. In the third iteration, left and right both point to 1, so the midpoint is 1 plus 1, / 2 equals 1. At this index, the value is -5, which is less than the index 1. Again, we move to the right half by updating left to mid plus 1, which now becomes 2. At this point, left exceeds right, meaning there's no fixed point in the array. Hence, we return -1 as the result. This example illustrates how binary search handles cases where no fixed point exists. To analyze the time complexity of our solution, we focus on the binary search process. Binary search works by dividing the array into two halves at each step. The midpoint of the array, mid, is calculated, and based on the comparison between ARR, mid, and mid, one half of the array is discarded. This eliminates half of the remaining search space in each iteration. The number of iterations required to reduce the size of the array to 1 follows a geometric progression, n/2, n/4, and so on. This process takes at most log2, n, iterations. Importantly, each iteration involves only a few constant time operations, such as calculating the midpoint and performing comparisons. When we combine these factors, the overall time complexity of the algorithm is O log n, where n is the size of the input array. The space complexity of the algorithm is determined by the memory it uses during execution. First, the input array ARR is provided as input, but since it is external to the algorithm, its size does not contribute to the algorithm's space complexity. Next, the algorithm uses only a small number of integer variables such as left, right, and mid to manage the binary search. These variables require a fixed amount of space, which is O(1). Furthermore, no additional data structures like lists or stacks are used in this approach, meaning the algorithm does not allocate any extra memory dynamically. As a result, the total space complexity of the solution is O(1), making it highly efficient in terms of memory usage. When analyzing the best, average, and worst cases, we notice different scenarios for how the binary search performs. In the best case, the fixed point is found immediately during the first calculation of mid. This results in a time complexity of O(1), because no further iterations are needed. On average, the algorithm performs approximately log2, n, iterations, as the search space is halved repeatedly until the fixed point is found or the search space is reduced to size 1. Therefore, the average case time complexity is O log n. In the worst case, there is no fixed point in the array, and the algorithm must exhaustively eliminate all possible search spaces, again requiring log2, n, iterations. Thus, even in the worst case, the time complexity remains O log n. To further understand the efficiency of this solution, let's compare it to a brute force approach. The brute force method checks every index I to determine if ARR I equals I. This requires iterating through the entire array, resulting in a time complexity of O(n). However, the space complexity remains O(1), since no additional memory is used. In contrast, our binary search approach leverages the sorted property of the array to reduce the search space exponentially. This gives it a significant advantage, with a time complexity of O log n and the same space complexity of O(1). By reducing the number of checks from linear to logarithmic, the binary search approach is clearly more efficient and better suited for this problem. The logarithmic time complexity of binary search is mathematically justified by its halving process. At each iteration, the search space is reduced by a factor of 2, leading to a logarithmic relationship with the array size, log2, n. Since each iteration involves only constant time operations, the total time complexity is O log n. Additionally, the algorithm uses only a fixed number of variables without allocating any extra memory, resulting in a constant space complexity of O(1). In summary, this solution achieves O log n time complexity in all cases, best, average, and worst, while maintaining O(1) space complexity. This makes binary search not only more efficient than a brute force approach but also the optimal choice for solving the fixed point problem, given the sorted nature of the input array. When working on the fixed point problem, there are a few common mistakes that candidates often make. First, it's easy to confuse the index I with the value ARR I. Remember, the problem specifically asks us to check whether I equals I, not to make unrelated comparisons or mix up indices with values. Another frequent mistake is overlooking edge cases. For example, you might encounter empty arrays with only negative numbers, or arrays where no element satisfies the condition I equals I. Missing these cases can lead to incorrect outputs or even runtime errors. Additionally, some candidates use a brute force approach on sorted arrays, iterating through each element to check the condition. While this works, it's inefficient, especially when binary search can solve the problem in O log n time. Lastly, assuming all values in the array are unique can lead to flawed logic. If there are duplicates, your solution needs to account for them explicitly, as this assumption isn't guaranteed in the problem description. Another mistake to watch for is mismanaging index bounds during binary search. Errors in calculating the midpoint or updating the search bounds can lead to infinite loops or skipping over valid indices entirely. Now, from an interview perspective, this problem highlights several key skills. One of the most important is recognizing patterns. Many problems involving sorted arrays, like this one, can benefit from binary search, and identifying this optimization opportunity can set you apart. Additionally, it's crucial to ask clarifying questions, such as confirming whether the array is sorted, whether duplicates are allowed, and what input ranges are valid. Interviewers also value efficient solutions. Be prepared to discuss the space complexity of your approach and highlight that this problem can be solved in O1 space. If the problem allows multiple valid indices where I equals I, explain whether your solution prioritizes returning the smallest index or handles scenarios requiring all valid indices to be returned. To deepen your understanding, it's useful to explore related problems that share similar techniques. For example, LeetCode 278, first bad version, involves binary search optimization, as does LeetCode 33, search and rotated sorted array, which adds extra conditions to the search process. LeetCode 852, peak index in a mountain array, is another binary search problem, but with a unique condition. And of course, LeetCode 1064, fixed point, is the exact problem we're addressing here. As for alternative approaches, the brute force method involves iterating through the array and checking whether I equals I for each index. While simple, this has a time complexity of O(n), making it less suitable for larger inputs. On the other hand, the binary search approach is far more efficient for sorted arrays. By narrowing the search range at each step, it achieves a time complexity of O log n. However, implementing it correctly requires careful attention to edge cases and proper management of index bounds. In cases where the array is unsorted, you can modify the approach with a linear search that stops as soon as a match is found. This has a time complexity of O(n), and while it doesn't offer any optimization, it handles unsorted input gracefully. This flexibility is useful in scenarios where sorting isn't guaranteed or when the constraints don't favor binary search. The trade-off here is efficiency, as it will always perform a full linear scan in the worst case, but it ensures correctness regardless of the input's order. By understanding these variations, you'll be better equipped to adapt your solution based on the specific constraints and requirements of the problem you're solving. Great job working through this problem. Today, we reviewed a simple brute force solution to the fixed point problem and discussed potential improvements. Keep practicing similar problems to sharpen your skills. Thanks for tuning in, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!